One of astronomy's great, enduring mysteries is what really happens on the inside of a black hole. We know that anything which gets too close to a black hole is ripped up and destroyed, thanks to its immense tidal gravitational forces. But if you were able to jump right inside of one, towards its very heart, then what would happen, and where would you end up? It is this spooky scientific question that has plagued scientists for more than 100 years, and thus it is going to be our topic today. Black holes are the most fascinating and mysterious objects in the universe. They are pockets of space which exist outside of the laws of nature, and are places where time and space as we know it cease to exist. What really happens on the inside of one of these universal boundaries remains a mystery, but among the possible explanations, there is always an inescapable one, which can neither be proven nor ruled out, the idea that black holes are gateways, to other parts of space, or maybe even to new universes entirely. Today, we will aim to establish what truly lies on the other side of a black hole. Bending spacetime to understand how a black hole could act as a gateway, you first have to understand the very nature of space and time. To date, nobody has understood this as well as Albert Einstein. According to his world-renowned and time-tested theory of general relativity, time and space are fundamentally linked, like two sides of a cosmic coin, combining to create a malleable cosmic fabric which lines the entire universe, known simply as spacetime. And we liken it to fabric because it is warped by the matter upon it. The plane of spacetime is curved by the presence of mass. Mass is a form of condensed energy, and where there is condensed energy, spacetime will fold around it, and the resulting effect is felt as gravity. The heavier and more concentrated the mass, the more the spacetime surrounding it will warp. And as such, if we compress enough mass within a sufficiently minuscule volume, then spacetime will deform so much that an abyssal, never-ending sinkhole will be created in the fabric. Within this area of warped spacetime, the gravitational influence is so great that spacetime itself starts flowing into the anomaly, carrying everything with it, including light. This results in a dark sphere around the area where light is being dragged into the gravitational well, known as an event horizon, and thus, we have a black hole. At the center of every black hole lies a spacetime singularity, a point so deformed by mass compression that it punches through the fabric of spacetime to become a physical boundary of the universe, a place where all light and matter meet their eternal end. In addition, a black hole also has a curvature singularity, which is the part where the curvature of deformed spacetime begins to take on infinite values. It is here where science begins to depart from general relativity and all our other models. If we were somehow able to survive up until this inside a black hole point, then we would experience something very strange. Time and space, as connected entities, would switch roles, as the black hole's interior becomes infinite. The singularity is suddenly no longer a physical point, but rather an inevitable event in the future. Space is so warped that all paths will inevitably lead us to this singularity, but time is so warped that we would require an ever-increasing amount of it to get there, as time on the outside slows down and eventually stops, forever. And so, at this point, our cosmic fate would be sealed. We would be frozen in that moment of time forevermore. The singularity now represents the infinite future of a featureless, timeless dimension, from which nothing will ever be able to escape. You would never reach the bottom of this sinkhole, you would just continue cruising deeper into your eternal cosmic chamber, unless you were to hit another part of spacetime. Wormholes and Einstein-Rosen bridges. We don't know what the implications of curving spacetime to infinity really are, so perhaps it is possible to curve spacetime all the way round, so to speak, so that a black hole may end up leading to a completely different part of space. You would then have a link between the two disparate regions which pinches them together, ignoring the cosmic distance between the two. Akin to folding a piece of paper to connect two dots, as opposed to drawing a line between them. You would have an Einstein-Rosen bridge, better known as a wormhole, a means for a black hole to subvert the spacetime continuum by acting as a portal. Wormholes are a fascinating prospect, and perhaps not just one of science fiction. While they've never been observed in practice, they are consistent with general relativity, and some scientists believe that they may be possible if not through black holes, then through cosmic strings from the earliest nanoseconds of time. But don't get too excited, because even if wormholes are possible, they almost certainly wouldn't be practical. Even if a wormhole bridge could form inside a black hole, it would be incredibly unstable. The immense gravity on the black hole's interior would constantly stretch and contract the spacetime bridge, before severing the connection into two regular black holes, perhaps only seconds after it forms. Furthermore, even if a wormhole could remain connected for longer, it still wouldn't be a practical means for universal travel, as all the points made about time stopping inside a black hole still stand. You would never be able to reach whatever lies on the other side of a wormhole, you would simply get stuck somewhere in the middle and age to death in the process. But just because a wormhole isn't suitable for traversing, doesn't mean that two parts of cannot be pinched together, for however long. It is not known what kind of black hole, if any, could create such a bridge. Perhaps not your run-of-the-mill collapsed star, as if that were sending its relatively limited mass into another part of space, it probably wouldn't survive for very long. But maybe supermassive black holes, which lie at the hearts of large galaxies and can be billions of times heavier than the Sun, could become so massive that they are somehow able to burst through into another part of space. We have no idea what such a bursting black hole would look. White holes like at the other end. But in any case, we call it a white hole. As the name suggests, a white hole is the opposite of a black hole in its most fundamental respects. If wormholes in spacetime really do exist, then, for all that goes in via a black hole, there must be another hole somewhere through which all comes out, even if it only exists momentarily. This would be a white hole. Where black holes consume, white holes would eject. Where black holes gulp, white holes would burp. The event horizon of a white hole is not a point of no return, but rather a barrier of no admission. Matter can only flow outwards away from the singularity before being ejected into space. However, this does not mean that a white hole would indicatively repel all the objects surrounding it. Presuming one was able to survive for longer than a matter of seconds, then like a black hole, a white hole would probably have properties such as spin, charge, and most importantly of all, mass, a mass capable of attracting other objects from a certain distance with its gravity. It is only when these objects approach the white hole's event horizon that they are unable to proceed any further. And so, far from being an unmistakably bright and bedazzling beacon, a white hole may actually look very similar to a black hole from far enough away, surrounded by an accretion disk, a network of satellites, and radiation. The one key difference is that a white hole would be expected to burp consumed matter and energy from its twin, instead of consuming it. However, this burping event would be tricky to spot, as it would not last for very long. If a white hole ejected too much matter too consistently, then before long its system would undergo a gravitational collapse, forming a black hole in place of the white hole. And so instead, it is more likely that a white hole's ejections would be highly infrequent and very brief. So, just to recap, we're looking for something that looks like a black hole, which may only exist for a couple of seconds, distinguished only by the fact that it burps, but we've no idea what that burp would look like. It's not a very useful profile to say the least. Needless to say, we've never identified any compelling white hole candidate in space. The billion-dollar question is that because they don't exist, or is it because they are exceedingly brief and rare, and thus we simply haven't managed to see one yet? Schwarzschild metric and the eternal black hole. Well, it's undeniable that white holes are very much a product of the mathematics of black holes. While a wealth of observations in recent decades have all but proven the existence of black holes, white holes have remained nothing more than a mere mathematical curiosity since they were first predicted in 1964. A few months after Einstein presented his theory of general relativity, in which he first predicted the black hole, a German scientist named Karl Schwarzschild solved the field equations for their first exact solution, giving us the Schwarzschild metric. The Schwarzschild metric describes the most simplified black hole which can exist, a single unit of compressed mass within a completely empty plane of spacetime, which is therefore unaffected by its surroundings. One which was never born and one that will never die, never growing or shrinking, an eternal black hole. It was from this earliest of case studies for general relativity that the white hole was extrapolated, almost.